So as usual, due to transportation issue, we keep talking, review the material before we continue. So as you know, we almost finished everything from this chapter. So basically what left is the Excel part. So we'll review and then talk about some Excel for today. So we will be hopefully we can start something new, but if not, then we are not being rushed because we are ahead of schedule. So rest assured, so we are okay. So let us very brief review. I'm not going to do a full review because I think I reviewed too many times. So random variable is just the way that you give number to outcomes, and the difference between discrete and continuous because of math issue. And I just for discrete, you can define a p, back p, which give you the you give me a number, I give you what probability that the random variable will give you, right? And this is well defined in discrete case. And the thing when big P can be converted to big F, they are the same thing. Okay, there's no difference between big P and big F in discrete case. And by stacking the big P to get big F, so there should be no issue. And then, but big P can be complicated. You look at the expectation, and one number is not enough. You look at variance as well. And the expectation is just the mean, and then follow the standard mean properties linear. Okay, and but the variance is square, so it doesn't satisfy the formula. It's not linear. Then you take a constant out, then you take squared. You add a constant, doesn't change. And also after that, we talk about a more than one number. Then you have a joint property function, and then you have expectation of sum with sum of expectation, and sum of the variance sum, but this only hold true for independence. If not, then you have the covariance. And then that go on, and everything holds for those formula also hold for continuous. And for the discrete case, then we study 5 different special type of distribution commonly known, and then of course there are many as well. If you're curious, you can look at Wikipedia or AI to ask you to come up with the thing that fit application, right? Because if you really go into property modeling, they just give you many more formulas, okay, that apply in various situations. And just to recall, the baseline for building this is Brunoni, which is only a binary view of the world is only success or fail. So only one you have once, so either you see one. And this is a big P, and this is En variance. And the binomial is also the same idea, but you repeat it n times, and each time independent. Okay, so it's just like you fix the maximum number of success, and then you count how many of them successful. So you already important part application is you already know number, right? So usually maybe number of days, right, which is fixed, right, and the number of days, and each day whether success or not, right? You have a predetermined n, then p is the success for each day, right? Then you can calculate those. And if you consider the case, in particular cases, n is super big, right? And p is the average success over the period of time, then that will give you a Poisson, right? And the Poisson is this formula. And in particular case, the mean is same as the variance. And we know how to do all this calculation. We'll do this today by Excel, tell you how to do every part without worrying about the exact calculation. Okay. And after that, we have the hypergeometric. That one is asking instead of every box to be open is going to identical, right? Every box is going to probably P. You have success or fail is fixed by destiny, right? You can imagine this is a fixed number of good or bad item. You keep taking items out, right? If you take one bad item, there's one bad item less in the total number of items you can draw. Same if you draw one good, then it's one good less. then what you get is turn out to be a fraction of combinations, right? And that is how you were able to handle the formula. And the P is rather complicated, but the mean and the variance is not too much different from binomial, right? It's just NP that MP minus 1 minus P, and then this the last term is just correction for because of finite sampling, and this is less than 1, so it has lower variance. And that's the example we gave already. And then last, we talk about continuous random variable. And we start by saying that P cannot be meaningfully defined because everything is 0 everywhere. So, but F is still well defined. So that's why I use F. And we learn this is the case, right? The big F is looking at what is the probability less than or equal to that value, right? And since it's so convoluted, then we learn the small f is a way to describe the big F. And the small f is saying that you look at area under the curve, okay? On the left of particular A will be the area equal to f of A. And the area must be 1 because this is the area is the probability. And in our study, the small f and the big F are the same way to say the same thing, same as the big P and the big F, right? Small f it can be, if you calculate area, it's the big F, right? And if you learn calculus, that actually you do integrate the small f, you get the big F, or you differentiate the big F, you get the small f. So if you learn the math, that is simple, but if you don't, doesn't really matter. I told you already what the implication, and that is what we call the fundamental theorem of calculus. If you really care, basically just this equation. But and because of f can be very complicated, right? The small f and the big F. So very often we look at the expectation variance as a way to summarize our P and F, sorry, small f and big F. And we learned 3 important continuous distribution that can be directly used in modeling of business situation, right? And the last 3 will be directly useful for our second part of our class. Okay, the first 3 you can use it to model without talking about data. Okay, same as the binomial, hypergeometric, or Poisson, you can easily find application in business. Okay, and the last three we will find application in our class directly. Okay, the first one, which is trying to demonstrate the idea of small f and big F, right? But itself is also useful when you don't know what the shape is, what kind of small f you can get. Then the best thing is you know the max, you don't mean. There's A and B, right? And then you can say, I don't know which should be the model. Then the easiest thing is, okay, every number is equally likely, right? Because you don't have an idea, then this f is very natural. And of course, the next thing you want to go is, okay, I have no idea, start from the initial uniform, then you use the base rule to update, right? Although I didn't teach you how to do updating when you're continuous, but the idea is the same, okay? But you would left it, if you want, you can ask AI or look at further classes to do how to update with the base rule with continuous random variable. You can do that, there's no problem. And the big F and small f, I think some of you asked me, do you need to know how area change from f big small f? No, it's not needed, right? Remember, what you needed would be the thing that in the green box, the green thing. You know how to do the green thing, then you're fine. Okay, and the purple thing is just for the theorem behind, right? So if you do the green thing, then the purple thing should not bother you anyway, right? And if you want to understand why your purple thing, you want to read this thing, the black or the thing we discussed. So if you know how to do the calculation, you're done, you're fine. Okay. But if you want to know more, you can go back a little bit to the purple slide, or then go to, if you still want to learn more, you can go to the black slide to understand what's going on. But otherwise, you don't have to worry about that. So the uniform, right? You probably should know this formula, right? Shouldn't be an issue, right? This is some formula we need to know, right? And you know these two formula, then you're done, right? So people, this is the thing we ask, right? Just like the example we asked you, right? I give you the rainfall is from 1 to 4, right? What would be the mean and the variance? You can know A is 1 and B is 4, then you can just plug in the formula, then you're done, right? Or you want to know the probability, then you just plug in, right? Between 1 and 3, we'll just f of 3 minus f of 1, right? Because just to remind you why this is true, right? Because this is small f. Sorry, it's uniform, right? Uniform is from 1 to 4, right? And the height is 1/3. Why? Because this distance is 3, right? Say for the area, the height is f, right? This is f. For this small f, right? The total area must be 1, right? The base is 3, the height must be 1/3, right? And you want the probability between 1 and 3, that means it's the area between 1 to 3 is this area. All right? The base is 2, the height is 1/3, is 2/3, right? Or you can use the idea that f of 3, right? Which is this guy, right? F of 1 is actually 0, right? Because it starts from 0. So basically you can just forget about this guy even, right? You can just CP about this guy, right? But just to formal to show you why I have this, because I just try to draw the parallel because next question is from 2 to 3. So I just try to make sure that you see what's going on there. Okay, that's why I have to take a difference. Okay, and exponential would be the case where it's a Poisson idea, right? Random arrival, but it's not number of arrival, but time until it arrives. So it's exponential. And the formula is like this. You can ask why you have E, because in this way, exponential means it's memoryless. In the sense that, right, if you recall, this actually means the following. F x equal, I know, k, okay, x k plus t is equal to f. This is fine. Okay. It means that once you have wait for k period, right, haven't happened, and wait for other t period the same as initially wait for t period. It just doesn't remember how long it waits if it doesn't happen. Okay. As I said, the example, right? The wife had been waiting for his husband for many years, and he still hold the same belief that her husband is going to come back tomorrow morning, right? So regardless of how long she had been waiting, right? So become a stone at the end, right? So that's what happened. So because how long had been waiting doesn't really matter. And this is just exponential, means this is just a downward sloping exponentially dropping very fast. This is what happened. And this is the formula, and look at the mean is 1 over lambda square, and this 1 over lambda for the mean and the variance number square. And that is how you calculate that mean at the mean of 20 minutes. Then once you have that, then you can calculate the lambda, because lambda is 1 over 20, right? And some of you may wonder how you get this number, right? Is it, I mean, of course, maybe come from engineer, maybe come from your data, right? The 20 minutes can be from your data. Your historical number is 20, okay? And then in order to in order to model, you just use your data to inform how you model it, okay? And you use the sample mean to map into this mean of this distribution, okay? And this is known as method moment. It's the way that you guess what the lambda should be. Okay. There are many ways to guess the data, but this is the easiest way to look at the sample mean. But you will learn this if you want to learn more, but that's how you get the lambda there. Of course, there are many ways to better use the data, but one easiest way is to actually use the data sample mean to give you this one. Okay. But this is out of the scope of a class to tell you how to do this. Okay. But if you learn learn further, you will learn how to get this number. At the moment, you can just simply look at the data. The sample mean is 20 minutes, and that's what you guess. That's the easiest thing to think. Okay. And this is how you calculate once you have the data, right? And I want to spend most of time to review the normal distribution because that is the key of I think this course as well. The whole highlight of this course is to handle very well how to handle normal. Okay. Because everything related for second half is normal. Okay. So normal is the bell curve, and if you still recall, the bell curve only have two things, mu and sigma square. Mu's control the location. Okay. The green and the blue just difference by the mu parameter. Mu tells you where the center of the bell is. And sigma tells you how spread out the bell is. The higher the sigma, the more spread out. And remember, the total area is 1. So the higher the sigma means the bell is less tall, right? If the sigma is very small, it's very condensed near the center mu, right? And this is the formula. And although I put the F here, no way I would ask you this one. So you can forget about this one, but I just keep here in case you would want to know this is normal, right? And this is give the example, and then the central limit theorem we will learn later, that will be important. Okay. And just to record it a bit, the kurtosis of the normal is 3. Okay. And the skewness must be 0 because symmetric. So that's the reason why when we learn chapter 1, we always compare to this, because normal is what we expect to see in many cases. So you want to check out if your data is different from normal or not too much. And we learn the shorthand notation for normal is n, a snake, and the n and mu and sigma square. And first thing we learn is no matter how we torture the normal, it's still a normal. The first way to torture it is to multiply and add, right? So you draw a number from a bell, you multiply by a constant, and a constant is still a bell. So which is not something usual in many cases. And I think for most of the things you learn, normal is the only thing that preserve this thing. Okay. At least for the thing you learn, only for normal preserve this. And because of the way that you do it, you can always shift the whatever normal to the standard normal and do all the calculation. Okay. Because the area mean the same. Okay. The statement has no difference. Okay. So when we do calculation, we use the Z table, and the Z table go from negative to positive. You can only use one version, or you can use both, which since you don't have limitation, you can use both. Why I have both? Because when you go to internet, you download, you have both, only one of them, usually. Okay. So that's why for your convenience, I put both. But if you happen to download anything, then just at least you can calculate by hand. Okay. So the first one, I just redo it again, is why you get this guy, how you read this one. Okay. Y less than 1.4, this guy, right? Less than just the F, right? It's the big F function, right? Big F is less than 1.4. So you can directly read the table. Big F is 1.4. Okay. It's actually here. This entry, right? Big F is less than 1.4 because 1.4, you read this row, And because 1.40, just this guy. Okay. And if I ask you probability that Z is less than 1.45, then you have to go to the fifth column. Okay. And similarly, less than 1.6, negative 1.6, then you go to the row negative 1.6, which is this guy. Okay. So this is the entry, then this number. Okay. And the next part would be between negative 1.6 and 1.4, right? So there will be difference between these two, right? The difference between the first bullet point and second bullet point would be the third bullet point, right? Because the purple one will be equal to the blue one minus the pink one, right? That's what you learn in kindergarten, right? You just remove the overlapping part, then what is left is not overlapped region. Okay. And because of Z table, we can show within 1 sigma, 2 sigma, 3 sigma, okay, is 68, 95, 99. Okay. So let's do the proof. Okay. Let's show you why this is 95. So you are 95. At least I show you the 2 sigma rule, why this 95. How I get this from the table. Okay, let's do it again. So the Z here is from 0. What is 2? What is this number? Okay. We want to know 2 above 1 SD above the mean and 1 SD below the mean, right? So that's what we want. Okay. But the data you have is just only this wiggling pink area. Okay. Because you only know less than 2. Okay. And less than 2 is what? Less than 2 is go up here. Less than 2 is this guy. 9772. Okay. So that means that the purple area is 9772. Okay. Now, then what about this blue area? Okay. What's this number? Look at negative 2. Okay. Which is 0.0228. Okay. So this area is 0.0228. You take a difference, that is very close to 95. Okay. That's why when it's between the Z is between 2 and negative 2, then it's actually 95%, right? What is Z? Z is how many SD from the mean, right? That's the definition, right? Because that's how you define the Z, right? So that means that your observation between 2 standard deviations from the mean will be 95%, 7% within 1 SD, and 95% between 3 SD. What does it mean for our business application? Okay. Suppose you are a fashion shop owner. Okay, you want to open a fashion shop in a new city. The question would be, you have to prepare different sizes, right? Not everyone has same size, right? Everyone have different heights or weight or the dimension, right? Then what's to prepare, right? How can you prepare the inventory, right? Then you can use this 70, 90, 68, 95, 99%. Suppose you want to cater for 95% customer. Then you look at the 2 SD from the mean, right? Look at the height of the city you want to go to. Okay. You have the mean there. Look at the SD there. Add 2 SD and minus 2 SD. That will be 95% of your customer. Okay. Of course, if you don't want to do that, use 1 SD, already covers 70%. Okay. So this would already tells you that what you should do, because a lot of this height, weight, IQ, right? As I said, follow normal nicely. So this is, you don't need to really worry about the normal. You don't need to worry about it apply because it always apply, right? For those situations, right? So that would be the idea, okay? The rule of thumb, just 2SD, include 95%. Now, and here we said is that's like how to go back. If I give you probability that what is the number, right? So you would look at the question like this inverse. I give you the probability, but I go back to ask what is the number that less than 95, right? So the question is the following. The bell here, right? This is 0, okay? The question is asking, what is this small number z such that all the left-hand side is 95, okay? For 95. And that's very simple. You just look at the entry in the table, which is closest 0.95, then you're done, okay? And it will be, if you look again here, it will be between these two numbers, 94, 95, 9505. So this gives you the result, okay, 1.64, okay? So you can do the same. You can do left and right, but just by complement rule. Just one subtract from that, that gives you the left-hand side, right? They ask the right-hand side, but subtract from it. So we'll be doing this very often, don't worry. You see this in the second half of the course, which means next week, right? But you will be working on it very soon, okay? So the next would be, if we not starting from the Z, which is unlikely the case, we're starting from the normal, right? Then how can we start, okay? And you know the mean is 20, the standard deviation is 4, right? So this question is asking x is less than 16, essentially saying what happened is z is less than -1, right? Because here mu is 20, x is here, 20 is here, the bell is like this, right? So this is 16. So that means that this is 1 sigma, right? Sigma is 4, right? So that is essentially same as, if you look at the z, this is just 0, and this is -1, because this is z SD is 1, right? Sigma is 1. So if you are asked about this area, we same as this area. So that is how you get from the x to z, because they're the same thing, right? So that's the math is already show you how you do the calculation. And same for, this is the graph I show here. Okay. Why this is flatter? Because the variance is higher, so that's why it's more spread out. So that's why when I draw x and z, I already have this in mind. Okay. Same when you have more than, and then this is going to be the same. I'm not going to repeat this one. Okay. So what is left is this another interesting case of normal, which we'll use very soon, the next week, okay, is if you add two independent normal, it's still normal. So the bell curve add bell curve is bell curve, and bell curve subtract bell curve is still a bell curve, okay? And do note that when subtract and add, there's no difference of the variance. The variance, the same, okay? It's the shape is still that flat. The only difference between add and subtract is the location of the bell, the center, okay? Is that clear? So that would be the thing we will be using next class, because you will see why with that, because x and y are sample. We're sampling from bell curve. This is what we assume soon, okay? And chi-square would be the idea that you would have draw a bell instead of multiply and add, right? It says you square, okay? And unfortunately, you square is no longer a bell, right? Something that you torture enough so it distorted enough. But this chi-square is sufficient interesting by itself, and because that actually later you will see it is tracking the sample, tracking the variance. Variance will follow this kind of chi-square related, okay? But anyway, let's see if you have n different this, you add together, it's called chi-square n. You just have one, it's chi-square of degree 1, okay? Basically, if you have a bell, you draw once and square, that's chi-square 1. If you have bell, you draw one, square it, and draw the other, square it, add 2 together, it's chi-square 2. And if you draw one, square, draw 2, square it, draw the third one, draw the fourth one, draw the nth one, every time you take one square, n together, add together, it's chi-square n, okay? So this itself has usage, okay? But in our class, we don't talk about it. If you look at textbook, they have talked about that already, but it's not, I'm not going to talk about this, but you can easily find there's a chi-square way to use it, but our class is not going to work on this one. We will be using this as a base, but chi-square look like this one. It's like similar to look like this kind of. When one is like go down, but when you have more, then it's like a bell. Okay, and turn out the chi-square n will be same, very similar to normal. Okay, and we'll be using is this very funny thing. Okay, we use chi-square in this dimension is with a fraction where the numerator is the z, right? Standard normal, and denominator is chi-square m divided by m and take a square root, and you ask, what are we doing? Okay, anyway, this is called a t, student t with m degree of freedom, okay? And you will later see m will be equal to n minus 1 later, and it's number of sample, okay? Later you will see why we do that. But for the moment, you can imagine t is simply look like a bell curve. It's actually a bell curve, but with a fatter tail, okay? If you take the t infinity, that is z, okay, standard normal. Okay? And basically the standard normal, you are getting fatter. Okay? You're getting thinner here, shorter here, but fatter at the two ends. Okay? And the more the m is bigger, the more closer to the standard normal. Okay? And turn out that if t is around 200, okay, that is almost the same as standard normal. And this, what number using at the bottom will be with the sample size. That means that in your business application, later you will see when the sample size is more than 200, you will be using the same as the bell thing. Okay, the bell will apply. Okay, so basically we said is when I have big data, okay, the bell curve is sufficient for almost all the purpose. So that's why we emphasize on the bell. Okay? But to understand why it holds, you have to see this. Okay. After this one, I talk about the other one that is turned out to be very important as well, the F distribution. We'll be using it the last class. Last two topics is to compare two different chi-square. And as I said, chi-square is the variance. And you want to compare variance, why? There are many reasons you want to compare variance. One is you just care about they're equal or not, because say suppose you are comparing two different stock, you care about whether the two stock have same risk or not. Okay, this is the first application. The second application is variance also measure the precision, quality of your product, right? And also you want to compare the quality of the product. The third is later you will see this kind of variance is trying to capture whether when you later estimate your model and your model is going to be meaningful is through comparing variance. So that's why you will see what we call analysis of variance. Because you are expecting if your model is useful, your variance of noise, right? The noise of your model must reduce. Okay. If your model is meaningful, your model should reduce some noises. So to check whether your model is useful, you should be able to do this, right? Because you want your model to predict precisely, right? Better. So you reduce your error, variance of your error. So that's why when you compare two different models, okay, and that's what you get, right? Because when you do prediction, right, you see whether your model is going to work. You want your model to do a good job. When do a good job, you have less variance in terms of the performance. Okay? But you'll be more clear later. Okay. But at the moment, happy with all this thing at the moment, right? This F look like this, and you come back, you see it, but you don't have to worry about the shape. Okay. At the moment. Is there any question? So I hope it's good review, and then you know what's going on. And in case, since we're done, we'll do Excel as well. I then I quiz 3 is already there, so you can have fun. And some of you have seen that quiz are slightly more difficult. Yes, I have to tell you that in terms of difficulties, quiz is the most difficult. The second most difficult is our assignment. The third most difficult is our exam. So it's decreasing in terms of difficulties, okay? So expect your exam is more difficult than your assignment, okay? So if you know, basically you mean if you know assignment, you should know very well about your exam, right? If you know the quiz, then you should know assignment, okay? And the assignment has also been released already, I think. Where's the assignment? Yeah. Where's my assignment? So assignment is also there. You're given 2 weeks to finish it. So I don't think we have a lot of questions. If you check, it's just like question 1 asks you to look at simple calculation, discrete random variable there. And then we have a binomial. And then we have Poisson. We have a geometric. We have uniform. We have exponential and normal. 7 questions. Okay. You have 2 weeks. Every 2 days you do 1 question, you're done. All right? So shouldn't be something too difficult. Okay. And I guess I asked the other section, they keep worrying about exam, okay, which I call it text. I don't call it exam, but it's okay to call it exam. And they are worrying, okay, I said, I don't have too much calculation, then what do I mean by not too much calculation? So I released my last year exam, 1 hour exam, you can see just only 3 questions. Okay. And this question, say question 1 have part A, look, it's not very complicated, right? I asked you how to calculate the sample mean and sample variance, right? And I have a question. This one you should know how to do it, right? From now, right? Exponential, mean of this and this. Use Excel to you don't need to give the answer, you give me Excel output, which you know it after the break, right? So be able to calculate that. Okay. And the third question is more like a base rule idea, right? You have team A have 30 developer and designer, and B have several developer designer. You pick some people. If one guy developer, what probably the guy from A, right? Something like that, right? So that's just a white ball and black ball. It's a box A and box B problem. You know how to solve it. Just to put it in a different way, right? Right, and then we also have this Q2 will be something you learn next week, okay? And Q3 will be doing some ANOVA will be this last chapter. That's it. So I don't know, 10 pages, 1 hour, okay? I mean, it's not something, the question is not very difficult, but If you don't know the material, then it's very difficult. If you know the material, then you just pick up whatever in your slide and you can just write down very quickly. Because I'm not expecting you can look at the question. It's not asking you to do a lot of things. Just like each question may be 2 to 3 lines. Okay, you got done. Okay, and if you know, then actually, if you're good enough, then probably people actually finish half an hour, less than half an hour. People 20 minutes and just go. Okay, but if you don't know, probably you will spend an hour still struggling. Okay, so it's not. Well, if you have studied M1, then probably you find it very easy. If you do in high school, you have to do statistics. But our class, we don't assume anything, so it can be challenging for many of you. Okay, still. Okay, so any question? Let me know. Okay. If no, 3 minutes, we can start Excel because start something before we have a break. Otherwise, we don't have anything new before the break, right? So that's something before the break. So let's do only this one. Okay. So this is doing what? So this is binomial. This is actually, if you remember, this is the P function, NCX, PX, 1 minus PNX. Okay. This is this guy. Okay. You give him the N, this guy, give the P, this guy, and X is how many success you want. Okay. And you put this in, you set false, will be, this is the P function. And what is true here is the F function, right? Less than or equal to. Okay. Is that clear what it is? Okay, let's go back to the example we have done. Okay. To show you that this is right. Okay. Let's go back to the binomial. So we are going back to the very old days. Okay. With this. Remember this spicy food story, right? The restaurant owner have 5 customers. Each customer have 30%. They like the spicy food. Out of which I asked our 5 customers coming in, the next 2 of them are like spicy food, right? It's binomial, P equal to 2, right? So let's do the Excel. Okay. I have binomial, okay? And I have N, P, X, right? N is 5, okay? P is 30% each time. X is 2, okay? I want to calculate P of 2. Okay. How do we do that? It just binom this, okay? You can see number of S, okay, is exactly 2 here, okay? Maybe I just use 2 to make sure that you don't miss it, okay? Trial 5, probability is 0.3, okay? And then this is the P function is the false, okay? If true, will be the F function, okay? Okay. If you don't believe me, you can do this combine, okay? 5C2, right? And then 0.3 raised to the power 2 times 1 minus 0.3 raised to the power 5 minus 2, right? This formula, same thing. Okay. So this is the P. Okay. And what's F? F of 2, right? F of 2 is just P0 plus P1 plus P2. Okay. So that would be just, why we ask F of 2? Remember the question. This is exactly 2. But he also want to know no more than 2, right? Because he want to see how many spicy food he want to do it. So you can see there's a free calculation is very tired, right? But if I have the F function, then we're done, right? The F function will be just same. binom this 2, 5.3, but now I have true. Okay, so this is the same result that we see. So that means that our calculation is very simple, right? Once we know binom this, then we're done, right? Of course, the mean and the expectation, you can do it easily, right? Is that okay? So if there are no question, then let's call it break. But before I do it, I just save this file in case we lost it. Okay? So it's a break of 50 minutes. And then we will continue our journey on the Excel. And I think we can finish the Excel. And then if we have still time, then we will go to the next set of slides. Okay, but I'm not sure you can do it, but don't worry, we are on schedule, so don't worry about that.
哦，好，呢個係你哋依家嘅係咪啊？哦，得。Yes, that all makes sense. I mean, yeah, it's hard, but
I have it. Oh, so it's one. It was like I registered. That was we didn't. I don't know. Where the
So you are good. So you had it.
This she came here. And then one said like income is the only bus her bill. She's like, oh, there.
So you guys have some benefits. Mean anything? So you guys have what happened. What's up? You are very high. Any of you make that, so this is good luck for you. Super tired. Oh, things you are. So, you know that those for my favorite. Retired. I am also like this. Why? Retired. They're all tired. You're looking things. Yes, good luck for you. Why? Yeah. Luckily, there's nothing, so I hope she didn't do anything to that. So, is my exam difficult? You can check. I mean, to be honest, if you look at your previous cohort, you look at the previous exam, and previous exam, and previous exam, they are all very similar. I mean, although I use almost similar exam each year, turn out you still have good distribution. So it's not so it doesn't really matter what kind of exam I give. It's always I already have a good distribution already. So so you will not seeing too much surprise from the exam. So you will be something follow we have done. So you can judge whether it's difficult or not at the end of the day. As I told you, the difficulty not lies on the question itself, but rather how fast you can finish it, right? If I give you 2 hours, everyone get 100 points, I think. Everyone get full mark. But 1 hour, I think is good enough to know whether you know or not, right? If you take time to do it's open book, right? So if you know it, then you can do it quickly. If you don't know it, then you are unable to do it. So it's not something like I have to make it very difficult. The difficult part is the time, I would say. So, but it's obvious, right? If you know it, then you should be able to do it. I guess it's okay. We are in the good shape. Next time I should ask a question. Are you very tired? I think that's the case. I think I should ask the question next time. Are you super tired? So we have normal, yeah, the graph, yes, T, yeah, this is a good one. Binom dist, that's it. I don't think we teach random distribution. We have random variable and distribution, but not random distribution. The speed is okay. And so don't worry, we are ahead of our schedule, so it's not, you don't have to worry too much. Yeah, the reason is you guys are too super good. We are far ahead of the other section, so I can't go too fast. Otherwise, but it's okay. I mean, and also some of you actually are very tired from the exam, so no point to rush anyway. But we will be very quickly finish this off, and then we can start something new, because it's very boring to go over Excel function, right? But at least I would try to go over some of them, right? So here is how you can have a P function being drawn in this way. I don't want to bother you with that, but that's how you draw the P and you how to plot this, okay? And this F, right? And since I'm not examining how to draw the F and P, but you know how to figure it out, right? So just how to use it. Okay. The next one is Poisson. Okay. Let me demonstrate the Poisson. It is 5 and 2, right? Remember the question, right? It's Poisson this x lambda. So go back to the Poisson question. Let me demonstrate that. Okay. Restaurant with 5 customers come in, exactly 2. Okay. So let me do Poisson here. Poisson only have one thing, lambda. Lambda is 5. X is 2. Okay. And P of X, P of 2, right? So next hour, 5% come in, and what happened to 2, right? So just Poisson this 2, 5, and then this is false. Then we're done. Okay. Now, the more interesting question will be, what's probability that 2 or less people comes in? The F is not in the example, but you can easily calculate that as well using the F function. Right? There's Poisson this 2 and 5, and then true. Okay. So this will give you that P of 0, P of 1, P of 2. Okay. So there's some tricky point here is, what is probability 3 or more people comes in? Right? And the thing that you calculate 3 or more people comes in, then you have to add P3, P4, P5, add to P infinity. Right? You can't really do it. So that's why you need to use complement rule, which is 1 minus the F2. Say, if you want to calculate probability that X is bigger than or equal to 2, given 3, right? 3 or more, then just 1 subtract this guy. Okay. This will give you the probability under Poisson 3 or more, right? Because you can't really add from 3 to infinity, right? Then you have to use this complement rule. Okay. That gives you an idea why the complement rule. Because 3 to infinity, you cannot easily do it. But 0, 1, 2, you can find it and subtract from 1. That's what you get. Is that okay? So once we know the Poisson, so we want to do the next hypergeometric. Okay? You have hypergeometric NA, NX. Okay? Let's look at the question again. Hypergeometric is here. Is XNAN. Okay? So you understand why I did use this notation, because this is happening in the Excel. Okay? It's not the easiest thing to see. Okay? Remember this question is, I have 30 computers in the warehouse. 4 of them are bad, 26 of good. And you draw 2 of them. So you draw 6 of them. Probably 2 of them are good. But 2 of them are bad, right? Because 4 are bad. Okay? So the hypergeo this. Okay? So let's hypergeometric. And 30. A is how many defective item? Is 4. Okay. N is 6. And X is 2. Okay. And you want to calculate P of 2. Okay. So just hyper to this. You put X. So you put 2 here. And then you put 6 here. And then you put is A or I forgot? Yeah. 4. You put 30. Then false. Oh, 6, 4. Oh, 30, sorry. Yes. Okay. So this is the answer, right? Of course, if you want 2 or less, then you can do the F, right? So if you want F of 2, right? So 0, 1 or 2, then you use the F function. So just being lazy, I just copy and paste and I change false to true. Okay. Then give us that 98% of the time, you should get 0, 1 or 2. Okay. And actually that we will see this underline the idea that if you get 3 items that are bad, then you would question whether the assumption you are making, right? Because you were told only 4 of them are bad. But if you have 3 or 4, which only happen in 2% time, nevertheless you get it, then you would wonder, someone told you that A is 4, is right. So that is the idea behind the audit, right? Is because N is total number of the thing you can verify easily. But A is something your financial statement or the client told you A is record, right? And N is your decision, and X is your outcome, you check, right? If you turn out that very unlikely, most likely is only 0, 1 or 2. If you get 3 or 4, something is very unlikely, right? 1% or 2% of time. Shouldn't happen. It happened. Then you would question the A, right? So that's why I said this apply to audit. Okay, that's how you apply your understanding to audit. Exactly here. Okay. So this is a discrete case. And once we're done, we go to exponential. Okay. Exponential, we use 1 over lambda as a mean. Just input the 1 over lambda. Or as I told you, they use beta directly. Beta is 1 over lambda. Just input that. And remember, continuous, we don't care about the F, but rather the big F. The small f is not something concerned. So we always do the true. Okay. So let's remember this question, right? You have 20 minutes for each one to come, right? And this is the first 10 minutes. This is exponential. We have a lambda. It's 20, right? Remember the question, right? What's 20 is for the period of time, how many people would come, right? If you remember this question, right? 20 minutes, right? It's how many minutes, how many time until the first thing arrive. Okay. So F of 10, right? How many people arrive in 10 minutes? Ten, 1 over 20, and then true. It's the same. Right? X is 10. But there's a question, right? Is that okay? And next is we talk about normal, and that's pretty much we're done. There's some T and also F as well. So normal, you have 2 things. Okay. You have this normal disk. You input the mu and sigma. Okay, not sigma square. You input the mu and the SD. Okay, and give the F, but we use the Z table. It's norm this mu sigma. Okay, but that's not a C table. It's X table, right? This is and then if you have norm S, will be the Z table we have. Okay, so let us show you normal. Okay, normal with mu, I don't know, 20, right? Sigma is 4. If you remember, x is 16, right? The question, right? It's 1 SD below the mu, right? We're asking what is the probability x 16, right? So that would be norm dist 16, mean is 20, standard deviation is 4, cumulative true is always, when you remember, well, continuous, you always use the true, okay? You don't have to worry about that part. Okay? So then we use the standard normal. So normal is even more simple. Z of -1, right? So f of -1, right, is this norm dot s standard. Just put a number -1, then always true, remember. Then we're done. Okay, because it's 1 SD below. Here you can see this is the norm dot s dot, this is the Z table. Just put in the number, then it's there. So in the exam, if I don't want you to do calculation, some of you ask me, what do you mean by I don't want you to do calculation? I will just allow you to write this. I will write that in the question. Then you can just don't have to worry about this. Okay. So I will try to give you almost all credit if you solve the right formula, right? Even though you don't solve the final answer, right? Then I think we should be able to give you almost full credit or even full credit, depends on how I set the question, right? So this is what we have, okay? And to show you the 2 sigma rule, it's like this, right? The 2 sigma rule will be f of 2 minus f of -2, right? Because that is the area between 2 and -2. So there will be norm this 2 true minus norm this -2 true, right? So this is the 2 sigma rule. Okay. So you can do 1 sigma rule or 3 sigma rule. You can see this is 95% is between 2 standard deviation. And the next thing is you want to inverse C, right? So this is the function. The last function we'll talk about is S dot inverse. Okay. Is norm S dot inverse. You put 0.95, it's 1.66, right? Remember what it is this guy. This is saying that I have a distribution here. The area up until 1 point is 0.95. What is this number? That is F inverse, S dot inverse 0.95, which is 1.644. Okay. So let me show you this formula here, right? Inverse F of 0.95. If you want to maybe do this one, -1, right? F inverse. So this is how you use this guy. Okay. So basically you need to know this the moment, okay? And this up to here, okay? And for the next two, I'm not going to work it out. I'll just go over that because you don't need it for your assignment at the moment, okay? The t and the chi-square, okay? And chi-square will be same, but you put the degree of freedom n over there. So you have this, false and true, and the inverse, okay? And the t also the same. You have to x, you tell me the degree of freedom df. And the f will have to tell me n and m, the same thing, okay? But you don't have to worry about this because we will use it, we'll tell you. Okay, but just telling you there is something like this. Is that a question? That's nice. We're happy. Okay, we are only 5 weeks. We've done half of the semester, so we are way ahead. So that's why don't worry about that. Okay, so we have enough time. If not, then some of you may ask if we have more time than we have some leftover. In the class we cover Python or R. We have time, of course. Extra material, you decide whether to pay attention, right? Because it's not examinable. We are going to test the additional material, but we go over the Python or R. It depends on you. I think I will do Python. That would be more useful for your future career. But I think we should have enough time, so don't worry about that. Only for this session. Other session is still on schedule, so we are faster. So at least we have 1 or 2. Maybe we have 1 or 2 classes more than the other. The other class also canceled because of the holiday. So that's why they will also cancel our 1 more class. So we will be far ahead. So don't worry about that. Now we're done. So I think you are ready to do your assignment. Shouldn't be an issue. 2 weeks. I think you should be able to do it very quickly. But I know you have midterm. In case you need extra time, let me know in the next you reply. Then we can extend the deadline. There's no problem. We can extend that because we are ahead of our schedule. So if you let me know, if you need more time, let me know. Right? Otherwise, we will just give you 2 weeks. Okay? Is there a question? Is there a question? Any question? No, we are done. We're done first half. Okay, now we're happy to go to second half. Second half is all about data. Okay? And so far, before we're talking about many things that have no data. Now we're talking about data, right? So far, we just no data at all. Now we have data. So that's why we talk about data. And data, the idea is called sampling. Okay? Let me give you the idea what we're doing. What is sampling? So population is the things we want to know. Okay? And for example, we want to know income or age in the city, people, how much they want to pay for your product, right? How many goods are defective, right? And things we want to know is your choice, okay? Suppose you want to know how many people in CHK like to eat mooncake, right? For example, I don't know what's a good question, but anyway, there's a question. If you only care about CHK, that's population, right? But if you want to care about everything in Hong Kong, all the university, then you will be in adult population. So it depends on your question, what you care, right? So that means that for your project as well, you will decide what is the population, right? Because you want your conclusion to apply to this group of people, that's population, right? You want to generalize your idea, right? If you are able to, you only care about the data in your firm, and that's the only thing you care, you don't care about the customer, you only care existing, then it's still okay. Okay. But if you want to include new customer, which not in the data, that will be in population. So it's your choice, your subject. You decide this one. But the question is, very often we don't have all the resources to study everyone in your population that is your interest. We will do a subset of population, a smaller group. Okay, that's a sample. For example, let me give you an idea, right? So this is the thing you care is called population, right? And the population were Mr. 1, right? And this is Miss 2, right? And this is Mr. number 3, the dog, right? And number 4 maybe a toy number 4, right? There will be many things you're interested in, right? Then, of course, we may be interested in all this, but you are unable to collect information for everyone, right? For example, you are unable to talk to the dog or the tortoise, right? So you can only collect this data, right? So the thing you can talk to, you can meet is subset, is the sample, okay? And of course, you can't arbitrarily talk to the sample you choose, because otherwise it's not useful. The sample you get have to be representative. So that's why you want, because why? Because it's a sample, right? You want the conclusion from this sample to shed light, to eliminate, to tell us what happened in the population. So as we know, garbage in, garbage out, right? So it must be, the sample has a meaningful thing to say about population, and this, the snapshot you get, should double the meaningful subset of the population. Okay? And to get the meaningful one, the sample, the best thing is you do random sample, which we will show next set of slide. Okay? Which set is you randomly pick up people. Okay? If you randomly make people, then the sample you got will be very meaningful. But how to randomly get people is not easy. For example, if I want to know people in CHK, okay, and I do a survey, suppose I do it in the library. Okay, I stand in the library at the front gate, okay, handing out questionnaire. If you fill in, I give you a chocolate, right? Okay, say for example, in that case, then am I able to get, is it a good sample? The answer is depend on population. If you look at people who want to go to the library, I look at everyone. Yeah, of course, right? If I do it every single day, or I do it 1 week, not the exam week, right? I just do it random regular week, right? Then I can say a lot of things about people who go to the library. But what happens if people don't go to the library? You miss them, right? Just like if you do a survey based on phone, then you only have the problem of getting the phone, right? Those people don't use the phone, then fails. Okay, that's actually a famous case in the US in the 1930s, I think. Yeah, 1930s. I think they have a newspaper at that time. They do the one of the largest survey probably in history. I think they asked about 1 million people, more. I think about at least 100,000, at least 100,000 phone call. They make a phone call, okay? Say, do you support candidate A, okay, or B? In the US, only A or B, right? Republican or Democrat, A and B, and over the majority people support Republican, okay, 60%, and 30% go to the Democrat. Yeah, and turn out, right, this last sample, right, then you would expect, right, the Republicans should won, okay, and turn out exactly opposite. Okay, you think they spend a lot of money asking so many people, right? They should be right. And you ask what have gone wrong. Remember, it's 1930s. So who have the phone? Those people who are richer, right? Not everyone had the phone. So if you only talk to those people, of course they support Republican, right? And the Democrat don't have anything, right? So that is the reason, even they do the largest sample poll in history. I know after that, no one had done that large. Okay. I mean, you look at the US, now they ask the political poll, 1,000. Okay. Well, I mean, 2 weeks later, you will know how to get the number. I'll tell you how to get the sample size for asking yes, no question. You can actually know what is the number you should ask. I think around 1,000 to 2,000 is already sufficient. Okay. If you able to get the data right randomly. But now making phone call is okay, right? Because almost everyone have the phone, right? But you can see there's a problem of getting a sample, okay? But in our class, we don't talk about how you generate a sample, okay? That is out of the scope, but you should think that your sample should be representing a population, right? Suppose you are going to collect data only on CHK. You want to conclude that hold for all thing in Hong Kong, all people in Hong Kong. Does it hold? Right? Probably not, right? CHK people are nicer, are more laid back, are more hardworking, right? I think, right? Compared to other places in, right? In Hong Kong, you people are more aggressive, right? More competitive, right? So that's what happened, right? So it's different, right? So let's go back. So that's important. So let me say again is we can use the representative, that's very important word, and use small picture, that's from the sample, to make a guess on the big picture. Okay, use small to say something about big. Okay, that's what the sampling. Data. We use data to make a decision. Okay. We call that is actually what AI is doing. The LM, they train by a large data set, but large is not large enough to cover the world, right? But it's large enough, represent enough to be useful enough for us to do all the thing, right? The large language model, right? Just like based on your poem, based on your history, they try to guess what's going on the next word, right? The same thing goes on here, right? So as long as that's why you see, right? When the AI trained in a nice way, you get the nice data, then they can train very well, right? If you get a rubbish data, they'll get the garbage out. Okay, so that's very important to get your data right. Okay, and that's why Google have a very good data, right? So that's why the AI is very good as well, and the Elon Musk also have a very good AI because he has a lot of data. Okay, anyway, so here we have some kind of math, okay, to understand how what we learned from the last class related to why we need to learn distribution, why we have to learn the small f or the big P is coming from here. Okay, we are going to imagine our population, the thing we want to study, can be represented by a frequency table. Okay, the frequency table by construction is our P, big P function, right? Or the small f function. Okay, although there's no probability, right? But you can also use the big P and big F to describe it, right? Because the relative frequency is just same as the probability, right? As we learn, right? If you draw one guy from that population, how likely you draw a particular guy is actually probability, right? So that means that when you draw one guy, it's actually follow the distribution, right? It means the following. If you draw and draw and draw, keep drawing, right? Draw many times, you actually recover the F, right? So that is the idea, right? Just imagine you don't have a die, imagine a die, 6 face, you don't know it's fair or not fair, right? You keep rolling, you get 1, 2, 3, 4, 5, 6, and you get, say, equal number, then you will know 1, 6 is each number, right? And then you can calculate mean and variance, right? So that means that imagine a case of here, right? Suppose this amount of food they eat, right? You can basically draw a distribution, right? X is number of food they eat, right? You can draw the F, right? F is the relative frequency there. You can figure out what's the mean here, what's sigma here, right? Need not be normal, but this is the idea behind. Okay. And a sample is just to draw a guy from there. You can draw more than one, okay? Some observation from there. And here, very important, the key is what we call random sample, which means that I close my eye, I pick up a guy, right? It can be guy number 1, or woman number 2, or dog number 3, or tortoise number 4, right? It can be anything, but you have to close your eye to draw. And because you draw, the very important key is when you draw, whom you draw is same from the relative frequency table, right? So just reverse what we do in the last chapter, right? Last chapter is, I know the F, I draw that, right? Now it's the same, right? It's just like I draw that from the known thing, okay? It's the frequency table. And the sample size n, I will write each observation x1, x2, xn, okay? And do note that these are all random variable. Why? Because before you draw it, you don't know what they are, okay? You actually draw from the big F there, okay? So you close your eye, you can imagine, right? You close your eye, you can draw number 1. You close your eye, you may draw number 2, right? You can number 3, number 4, right? Depends on how much food they eat, right? You can draw, I ask how much food they eat, right? So it depends on who you draw, right? You may be drawing, because random sample, you may be drawing number 1 many times, right? You can draw number 1, 2, 1, 2, 3, 4, 4, can draw the same, right? Because random sample means every draw is the same. So you can draw the same guy. That is allowed. Okay. Okay. If you don't allow that, that become what? Hypergeometric, right? You draw the same, it's actually the binomial idea. Okay, you draw the same guy. You can draw the same guy. Okay. So here, if you don't like the math, don't use the math. This is the idea. Okay. If you don't like the technical slide, right? You just remember this simple random sample is the most basic thing you would draw. This is very difficult to achieve, but assume we can do it. Okay. Is each element or each observation have equal probability being select, everyone have same chance, and when you select, they're independent. When independent means that you can choose the same guy again, and again. Okay, it's possible. Okay, is that clear? And of course, this is not easy. Okay, you can see it's not something, but of course, when the n is large enough, that's okay, right? Because imagine you do a telephone survey, if you call the same number again, you got banned because you are harassing people, right? So you are not allowed to keep calling the same guy. Even the random number tell you call the same guy, you are not allowed to do it. If you do it, then probably the police will lock you up, all right? So you can't really talk to the same guy, okay? But we try to achieve that. So technical terms, right? If I say simple random sample means each observation is an independent random variable, and they have the same probability function P or F, okay? Depends on discrete or continuous. Okay. Now here is some property. It's not surprise to you. If I have population with mean mu and variance sigma square, do note that these are hypothetical. We really don't know this, right? If we know, then we're done, right? We have to do this. There's just some number there. We don't know, but there's some number there, okay? But if we are going to collect some data, we went down to pick up people, okay? And on average, okay, each one would have the mean mu. That means that if we collect many, okay, potentially, you will get back the mu. That's the idea. Is that clear? So if you have many samples, later you will see this is what we call law of large number, but we will save it for next class. So that is very important, called LLN, law of large number, is if you get large enough sample, okay, then we keep sampling, then the sample mean will be the population mean, okay? There will be no doubt, okay? And here is the variation of each one is this guy, okay? But still, we don't talk about how to guess this guy, okay? Just remember, this is unknown, right? So we just know the variation of each observation will follow this guy, okay? And covariance 0, which means that I tell you the number of one guy, doesn't tell you the number of the next guy, okay? As I said, right, you pick up a tortoise, doesn't tell you the next one is a tortoise or not, or a rabbit or a man or a cat, doesn't tell you anything, okay? There's no indication on the next one. Because independent, right? Independent. So that's very important later you see. Okay. Actually, simple random sample is even stronger because it means that beyond mean, variance, covariance, it actually means the same distribution, F, or the big F or the P function, which means that then the same median, same mode, same IQR, same skewness, same kurtosis. Okay. Everything is same. F is also the same. Okay. And you would ask, is simple random sample is simple, but it's very difficult to do in practice. It's almost impossible to do it, I would say. Okay. And for example, as I said, online survey, some of you would do, right? But senior people don't know how to use the phone, right? Let alone internet, right? If you give them a very complicated Google form to fill in, probably they don't know how to do. Okay. Or many offline survey, I told you, right? if I going to stay in the library, or I just in the MRT station, right, subway station, I just stay there, I will meet some people, right? Because people who drive to school would not be in my sample. Or people walk from the campus inside, they will go to the subway station, I miss them. Right? Or some people take the helicopter, right? Then I will not be able to get them, right? And that means that you have to use many ways. It's called some advanced sampling method. For example, with the stratified sampling, which is often people use it. Okay, you particularly look at how many men you should ask, how many women should ask, right? In CHK, we have more women than men, right? And if your sample have equal number of men and women, then your sample is biased. You have to give more weight to women than men. That's actually what happened in the real world. In the US, turns in general is more Democrat and Republican. So when you do the data, usually it's half and half, but you have to reweight a little bit. So it means that the weighted sum is like you allow the Democrat one, they say yes, the value of yes is more than the value of Republicans say yes. Okay, there's some way to do it, but it's way beyond our class. Okay, or you can imagine in the world, right? You would say in geographically, say suppose you know CHK has more students than other school, right? So you have to collect more sample from CHK and less student from Linnan or CTU, right? So that is the idea, right? It's proportional to the population, right? Suppose you want to know college student, right? Then different college you do different thing, right? In CHK, right? The old traditional classical college have more students than other new for college, right? So you can't have the same number for each college. Okay, you have to get more number from all the bigger college. Okay, so that's the idea, but it's beyond the scope of our class. So just leave it here for you to know. Okay. So our last slide is our class name, statistics. Okay, we learn halfway. Well, now we learn what statistics. Very surprising. What statistics? Right? Statistics is the following. It is the function of your sample. Sample is a random variable. So what it is the function of random variable. It is random variable, right? It's a formula, right? For example, what is statistics? Mean is a statistics. What's mean? Mean is adding up each observation divided by n. Remember what's different here from the last class? So from topic one is, in topic one, there's no random variable. You only have observation, right? But now we learn that what you observe is not something you have seen, right? You are trying to get is a random variable. Okay? In the topic one, we assume everything population. There's no sample idea. Here we have sample idea. So we are thinking that we get something is one possible universe we are seeing. Okay? So what we see the sample mean sample variance in the first topic is a statistics. So whenever there's a function means a rule, right? You add them up divided by n, or you do an operation, then it's called statistics. Okay, so we'll talk about that next week. So, and statistics. Okay, I will see you next week. Enjoy the weekend. Remember your assignment, your quiz, and good luck for your midterms. If you need anything I can help, feel free to get more, to add more energy to your brain. I will see you next week. Enjoy the weekend.